So let's continue with drawing pictures of molecules. Remember, the question that we're answering was posed a couple videos ago or a couple of pages ago in your pre-lecture notes. The question said to draw detailed pictures of the following showing orbital overlap that leads to bond formation. And what we've seen in the last few examples is that sometimes we have to hybridize orbitals to get the right shapes. Now, the first video, that was completely new. Maybe you anticipated me a bit more in the second one. I'm hoping you're going to anticipate me even more on this last example. The molecule we're going to look at is C2H2. And to know what kind of hybrid orbitals I'm going to use, I need to know the shape. Hybridization is just a game I play to explain the shape. To know the shape, I need the Lewis structure. So you might want to pause the video and get the correct shape on your page. I'm just going to jump right to it. At your leisure, you will find that this molecule has a triple bond, and around each carbon there are 2 electron pair domains. Now, that means we've got a linear geometry. And that is equivalent to saying, in terms of hybridization, that we want to have 2 equivalent hybrid orbitals. How am I going to get 2 hybrid orbitals? I'm going to mix 2 unhybridized orbitals. So, again, I'm going to start with the unhybridized orbitals from an isolated atom, and then we're going to blend it. Now, I want 2 electron pair domains. I want 2 equivalent orbitals, so I'm going to blend 2 unhybridized orbitals. And when I blend 2 orbitals, I get 2 orbitals. This time, the energy comes out exactly halfway between the S and the P because I've weighted 1 of each. The way we name the hybrid orbitals is by determining how we made them. We blended an S and a P, so this makes sp hybrid orbitals, and there are 2 sp hybrids in a set of sps. That left 2 p orbitals that we didn't hybridize. So those are the hybrid orbitals we'll use in this molecule. These carbons are both sp hybridized. All right, let's see if I can draw that. Now, I will attach a bit with me showing you with the models next, but let's see what I can do just from the basic principles. So, for C2H2, I'm going to take an sp hybridized building block for each of the carbons. And what do they look like? Well, every hybrid orbital has the same shape. Great big fat front lobe, little tiny back lobe, I'm not going to show. What differs from hybrid orbital to hybrid orbital is the angle between the hybrids. 2 electron pair domains as far apart as possible. That makes it linear. That makes the 2 orbitals directly across from each other. Coincidence? I think not, because the only reason we're hybridizing these is to account for a linear geometry. Now, those are the 2 SPs. Where are the leftover p orbitals? One of the p orbitals I'll draw straight up and down. And those 2 lobes together are a single p orbital, remember. The p orbital I drew perpendicular to the hybrids. That's always the truth. Now, where's the last p orbital? It has to be perpendicular to the hybrids, and p orbitals are also perpendicular to each other. So the remaining p orbital is going to be coming straight in and out along the z-axis, which I have to draw a little bit out to the side, just like in math class. Now, I'm going to make a triple bond between this carbon and another one that's also sp hybridized. And the first bond, I'm going to have an end-on overlap between the hybrid orbitals. That makes a sigma bond. Where's the other sp? Directly across from it. Linear geometry. Okay, for the second bond of the triple bond, I'm going to make a pi bond. And you remember that pi bonds are formed by the side-to-side overlap of p orbitals. So that means I'm going to put the p orbital on this carbon lined up side by side with the p orbital on the first one. And if we overlap them top and bottom, we make a pi bond. So there's the second bond of the triple bond. What I haven't shown yet on the right-hand carbon is the third p orbital. And because it's perpendicular to the hybrids and perpendicular to the other p, it's going to be pointing straight in and out along the z-axis. And hey, look, now it's side by side with the p orbital along the z-axis on the other carbon. So those two can overlap in the front and in the back. And those two regions together make another pi bond. This triple bond then is a sigma and 2 pi's. And I can make an even more generalization than that. Whenever I hook atoms together, the first connection, the first bond will be a sigma bond, and any additional bonds will be pi bonds. Now we're almost done. I've got the carbon-carbon triple bond there. Now I've got to make the carbon-hydrogen bonds. Hydrogen's going to use its 1s and overlap end-on. And remember, I said the first connection between any two atoms is an end-on overlap to make a sigma bond. So the first connections between those carbons and hydrogens were sigma bonds. Now, again, why are we dealing with this theoretical stuff? Remember, I said that this is going to let us predict the reactivity of the molecule. When I showed you a molecule with a double bond, I said it would react, whereas the single bond wouldn't. The pi bond of the double bond was the reactive bond. So guess what these are going to do? Now that I've got 2 pi bonds, this will react to do twice what the molecule with a double bond will do. Pretty cool. Now, I'm not the world's greatest artist, so I'm going to insert a little clip of me showing you this with my models. So now I'm going to use an sp hybridized atom to explain triple bonding. Before I do, here's something I should have told you before and haven't already. Really easy to know what kind of hybridization if you know how many electron pair domains you have. What we've seen so far for 4 electron pair domains, that's a tetrahedral electron pair geometry. That's the same thing as saying that it's sp3 hybridized. And how many sp3 hybrid orbitals come in a set? 4 of them. When I have 3 electron pair domains, that's a trigonal planar geometry. And that's exactly the same thing as saying that it's sp2 hybridized. How many sp2 hybrid orbitals in a set? 3 of them. Now we're looking at 2 electron pair domains, linear electron pair geometry. What kind of hybrid orbitals? sp. And how many sp orbitals come in a set of sps? 2 of them. So here is my sp hybridized atom. Don't worry about the color coding for now. The 2 hybrid orbitals, which are really fat lobes, I can only show little sticks with my model kit, are at 180 degrees to each other. Coincidence? I think not. We were doing this just to explain linear geometry. So there's one hybrid orbital, another hybrid orbital. The leftover orbitals are p's. One above and below, those 2 lobes make 1 p orbital, and the one front and back, that makes another p orbital. So as always, 4 valence orbitals. 1, 2, 3, 4. I'm going to hook it to another sp hybridized atom, and now you can see why I color-coded it. This black is going to be for the carbon-carbon sigma bond that I formed end-on, and the white is for the carbon-hydrogen sigma bonds when we're done. So I've only accounted for the first bond of the triple bond, the sigma bond formed end-on. Whenever I connect any two atoms, the first connection between them is always a sigma bond, and any additional ones will be pi bonds. So, how am I going to make the second bond of the triple bond? Well, these p orbitals that stand up and down can overlap top and bottom. And when I do that, that makes a pi bond. And remember, the pi bond has two lobes. The electron pair that lives in the pi bond could be anywhere in this loop. That's two bonds, sigma, pi. The third bond is another pi bond. These p orbitals are coming in and out on the x-axis, but they're lined up side by side, so they can overlap front and back. Front and back. So there is the triple bond. Sigma, pi, and another pi. Pretty cool, huh? And now, just because I'm not the greatest artist, let me show you the cartoons that the textbook shows you. Again, the hybridization we got when we mixed an S with a P. And we got a set of two sp hybrids that were directly across from each other. And when we put those together on the same coordinate system, that's the sketch of the SPs I was trying to draw for you. Now, to put that together to make the triple bond, this is what I was trying to show you with my artwork. Figure A there shows exactly what I was trying to show you, that the sigma bond was formed by the end-on overlap of the hybrids, and here's the up and down P overlapping to make a pi bond, and here's the front and back P overlapping to make the second pi bond. But as I showed you earlier when I showed pi bonds originally, I've been sketching those p orbitals a little too skinny. Really, they're broad enough that they overlap side to side and make pi bonds so that the electrons in a pi bond can move anywhere within that loop. You can also see the second pi bond looking the same way, but in the perpendicular plane. So now I'm ready to summarize what kind of hybridizations we have. And this table looks just like the same table we did to assign geometries, but we just added a column for hybridization. When I had two electron pair domains, that made a linear geometry. And a linear geometry means exactly the same thing, and all that it means is that it's sp hybridized. Two electron pair domains, that's an s and a p. And how many sp orbitals come in a set of SPs? Two of them. If we had three electron pair domains, we put them at the corners of a triangle and we called that shape trigonal planar. In terms of hybridization, what that means and all that it means is sp2 hybridized. And see, I've got one s and two p's. That's three orbitals I combined to make a set of three sp2 hybrids. Now what this picture doesn't show is the leftover p orbitals. We've got the hybrids, but where are the leftover p's? When I make a set of sp hybrids, I have two p orbitals left over. One up and down, and the other in and out. When I do sp2 hybridization, I've already blended two of the p's, there's only one left over. And remember, I told you that the p is always perpendicular to the plane of the hybrids. When I drew an sp hybrid for you before, I had that tilted on its side, but now that the sp2s are in the plane of the screen, perpendicular to that would be a p orbital coming straight in and out. So there's an sp2 hybridized building block. When I get to 4 electron pair domains, I have to blend all 4 of the orbitals, the s and all 3 p's, to make sp3 hybrids. 4 electron pair domains tetrahedral, 4 electron pair domains sp3 hybridized. Tetrahedral means sp3 hybridized, and vice versa. That's what it means. That's all that it means. Now, because I blended all of the 3 p orbitals in to make the hybrids, there are no leftover p orbitals. And these are the 3 geometries I looked at with you in detail. But with VSEPR theory, we saw we could also have 5 electron pair domains and 6. So you could probably believe me if I told you to get 5 equivalent orbitals, I'd need to blend 5 unhybridized orbitals, sp3 and 1 of the d's. And you remember we said we could only exceed the octet if we could use the d orbitals. Look, we're using the d orbitals. How are those orbitals arranged? To make a trigonal bipyramid. Coincidence? I think not, because our whole purpose in hybridizing was just to explain shape. Last geometry, 6 electron pair domains, octahedral. And I'm going to have to blend 6 orbitals to get it. An s, 3 p's, and 2 of the d's. And those are all arranged at the corners of an octahedron. Coincidence? I think not. So let's write down a few notes based on what we just saw. If I have an sp3 hybridized atom, what geometry is that? Well, I've blended 4 orbitals, 4 electron pair domains. sp3 hybridized means tetrahedral electron pair geometry, and that's all that it means. I can extend it a little further, though. Suppose I had an atom like carbon in the second period that couldn't exceed the octet. If I had 4 electron pair domains and the carbon has to make 4 bonds, that tells me that an sp3 hybridized carbon has only single bonds. Okay, sp2 hybridized. You're going to anticipate this. How many orbitals did I have to blend to make sp2 hybrids? So what's the geometry? I blended 3 orbitals, which means I have 3 electron pair domains, which means it's a trigonal planar electron pair geometry. That's what it means. That's all that it means. Now, if I had a second row element, like carbon, say, and I wanted 3 electron pair domains, well, carbon's going to make 4 bonds altogether to make its complete octet. If I'm spreading 4 bonds over 3 electron pair domains, then one of those bonds would have to be a double bond. Now, I'm using carbon as an example. It's a pretty common one in organic chemistry, but that's true for any atom where the octet rule is satisfied. Carbon, nitrogen, oxygen, any of those second row elements. Where is my pen here? If octet rule satisfied. Finally, you're way ahead of me on this last example. If I have an sp hybridized atom, what's the electron pair geometry? I've got 2 orbitals blended, 2 electron pair domains. That's a linear geometry. And if I had an atom that obeyed the octet, that it wanted 4 pairs of electrons spread over 2 electron pair domains, that might well be a triple bond. Usually, there will be exceptions to that, but not to worry about it. All right. Now, I made that look all pretty complex. Let's draw back and see if we can see the forest for the trees. I'm going to ask a simple question here. What is the hybridization of each carbon atom in this structure? And it comes down as simple as this. Suppose I was talking about this carbon here. How many electron pair domains does it have? 2. What's its hybridization? sp. 2 orbitals, 2 electron pair domains. Pretty cool, huh? What about this one? What's its hybridization? 4 electron pair domains, sp3 hybridized. What about this one? 3 electron pair domains, sp2. I blended 3 orbitals. And that's also true for this atom and for this atom. So I showed a lot of detail in my discussion, but that was a lot of explaining as I went. When I say draw the orbitals, I don't need you to draw everything that I drew, right? Just answer the question part of the question and we're all happy. And I will see you in Zoom class with my model kit.